Okay, let's look at another example problem. So I'm just going to set this aside. In fact, I'm just going to set all these over here. Start brand new. It's going to be page 6. Trying to keep these organized for me in case I happen to need them for later. Page 6 of lecture 3 and 4. This is going to be another example problem. Right. You can find problems like this in the text. This one says, if you read the problem statement, it says something about a fan is used to accelerate still, sometimes it likes the word quiescent, it's basically saying stagnant or still air, into a duct, into a square duct. So we got a fan over here, right? Electricity, right? So electrical plug, terrible drawing. You guys see how awesome my drawings are? I don't expect you to draw awesome, okay? I don't expect awesome drawing. I just expect you to try, right? That's really all you have to do here. So the problem statement will say something about a fan is used to accelerate still or stagnant or quiescent air into a duct. The duct has measurements of 3 foot by 3 foot. So this is an English unit problem. And so a 3 foot by 3 foot square duct. And it's pushing that air through here pretty good at an average speed of 22 feet per second coming through the duct. Right? So what it's saying, and what it wants you to do, let's do that. What it wants you to do is it wants you to find the I'm sorry, I'm looking for something here. It wants you to find the power input going into the fan, right? So I've got electrical power going into the fan right there. It wants to know what is the minimum power input required into the fan to cause this to occur. Now they've given us some things in the problem statement, right? So I've not read the entire problem statement back to you here, but the problem statement would say, well, you've got air with a density of 0.075 pound mass per cubic foot. Right? And so they're telling you that the velocity within the duct, we'll say, is V2. That's 22 feet per second. They're telling you that the air in the room, it's pulling air out of a room that's stagnant or still, so it's basically not moving when it goes into the duct. Back over in here in the room, it's not moving, but as it's moving through the duct, it's coming through at 22 feet per second. They've given us dimensions of the duct, so we know the area of the duct is 9 square foot. That's 3 foot by 3 foot is 9 square feet. So these are the things that are given to us, okay? And they want to know what is the minimum power input required to achieve this, okay? So we're going to have to make some assumptions, but let's say, how do we get there first? Well, here's what we want to know. If we want to find a work term, an energy term, a good place to start with that is the first law. Okay, so I'm going to say let's find the power input, or maybe even let's find the energy input, right? Just the total rate of energy input here. Okay, that's really what they want to know, is how much energy is this fan at minimum going to have to consume? Well, the first law says that the rate of energy in is equal to, energy in minus energy out is equal to the change in the energy of the system. Okay? Or we could say that this is equal to the rate of energy in minus the rate of energy out is equal to the change, the rate of change, the rate of energy change for the system. So if I put dots above everything, that's okay. That's not necessarily breaking any rules. Now, so to find that, and we say, okay, what are the types? What are the things that are putting energy into the system? And what is the system? Well, the system is the air in the duct. Right? The system we'll call the air in the duct. So what energy is being added to this system? Well, the electricity in it. Now, what's coming out of it? Well, it might be losing some heat, right? And there might be heat coming off of the fan, but they didn't give us any information about that. I don't think we're going to have any tools to worry about the heat transfer right now. And they really just want to know what is the minimum energy in. So if I worry about how much of this gets converted into heat, that's additional work I'm going to have to put in. So I'm just going to, again, because I don't know the heat transfer right now, and until we get to chapter 4, if they're not asking for the heat and you don't have any good way to find it, let's just assume that it's 0 for right now. They want to know, they want to know the work in, so let's not worry about the work out, because I don't see anything doing work, extracting work from the air here. So I guess what I'm saying is the only thing putting energy into the air is this fan, and it's using electricity to do so. Okay? And so as that air moves through, I can say we'll take the mass flow rate of the air times the kinetic energy. Because it looks like the duct is horizontal, and they've not told us any different. So we're going to assume the duct is horizontal. And kind of like with the heat transfer, right? Because again, this change in the energy can be, the energy of the system can be internal energy, it can be potential energy, it could be kinetic energy, it could be any of those three. So we have to say, all right, well, what about these other two? Well, we don't know anything about the internal energy. That'll be chapter 3. So unless they're asking for the change in internal energy, realistically, I would need to know the temperature change from here to there to figure out the change in internal energy. We'll talk about that in chapters 3 and 4. But right now, we don't know that. So we're just going to have to make the assumption that this is the same. If they wanted you to deal with an elevation change, the change in potential energy, they would have given that to us. So we're just going to assume, and this is going to be V2. Right? You could say V2 squared minus V1 squared if you like. That's not going to hurt anything. So basically what's happening is this fan is consuming electricity, and to do that it's changing the kinetic energy of the air from the inlet to the outlet. And we want to know what is the minimum amount of electricity required to change the kinetic energy from the inlet to the outlet from a 0 velocity up to up to 22 feet per second squared, or feet per second. Okay, so how do we get there? Well, what do we not know? We know the initial velocity, right? We've made assumptions to simplify the first law equation, which, you could write this whole thing out and say, well, this is Q dot in plus the power in minus Q dot out minus the power out is equal to M dot times U2 minus U1 plus V2 squared minus V1 squared over 2 plus G Z2 minus Z1. You can write the whole thing out. That's okay. All right, and then say, all right, well, we're going to have to assume those are 0, and assume this one's 0, and we're going to have to assume this is 0, we're going to have to assume this is 0, and that's all that's left, and then you write this down. Or you can look at your diagram and say, what's going on? Either way is fine. You can either write the whole thing out and cross out the things you don't know and that you're going to have to assume are 0, or you can look at your diagram and say, all right, well, what's actually going in? That's the left-hand side, is what's going in minus what's going out. And the right-hand side is the change. Well, what's changing? What energy is changing? The kinetic energy is changing. We have no way of computing a potential or internal change right now, and it's not asking for those. So this is what's left. So again, the power input is equal to m dot times the change in kinetic energy. So what's known? Well, we know the speeds. We're looking for the power input. 2 is just a constant. I don't know m dot. How do we find m dot? Well, you go back to your notes and you say, how do I find m dot? We say, well, there's a couple of things. If you know the density and the volumetric flow rate, that'll get you there. If you don't know the volumetric flow rate, we can find the volumetric flow rate as the product of area and speed. Well, we've got all that. Right? We know the area of the duct. That's a 3 by 3 square duct. We know the speed of the air flowing through is 22 feet per second. That was given to us. So I can find this, right? So m dot then is going to be, they've given us a density. And they were generous enough to do that. Let's kind of box this in. Alright, so the density they've given to us is 0.075 pound mass per cubic foot. Have your calculators ready. I'll work this with you, but have your calculators ready always. 9 foot squared. And then 22 feet per second. That's my speed. So my mass flow rate, pull the calculator out here. I have to move kind of quickly here because I'm going to be real short on time for this video. That's going to be 0.075 times 9 times 22. That's going to be 14.85. And the units left, so I've got cubic feet and cubic feet, so I've got cubic feet over cubic feet, so the units left are going to be pound mass per second. Okay? So the power input is going to be this. I'm going to plug this in here. It's going to be 14.85 pound mass per second. Multiply by, you don't have to write the units in your calculations, but I'm going to try to save you a lot of time later and say if you mess up, you don't get the answer that's in the solutions manual, or your answer doesn't match Chegg or one of your classmates that you're comparing with or helping and studying together. When you get something that doesn't make sense, the first thing you probably want to look at is your units. Do your units make sense? And if you don't have your units written down, it's going to be hard to trace out a unit error. Those 80% of your errors are probably going to be unit errors. So I'm trying to save you some time later. I'm just suggesting write your units down, but I don't require it. So when I've got this mass flow rate, I'm going to multiply by 22 squared, and I'm going to divide by 2. So we get an answer. We get a number there. Oh, sorry, you didn't see that. I got a number there, 3593.7. Now that's just a number. Numbers without a unit it doesn't mean anything to us, right? In fact, they're very dangerous. They can kill people, literally in our line of work. Unit errors can kill people. I know I've got pound mass. I've got feet. That's getting squared. And I've got per second. That's getting squared. And I've got a per second here. So this is pound mass, feet squared, per seconds cubed. All right? Looking at my timer there. So what do I do with that? Well, that's not power. What units would we like? Well, I'd like watts or I'd like horsepower. So how do I get there? Well, there's a couple things I can do. 3593.7 pound mass, feet squared, per seconds cubed. Remember the first day, I said there's this conversion factor. I could say 1 pound force, second squared, for every 32.2 pound mass feet. That is a conversion factor. Anytime I've got pound mass and I want to go to pound force, this works. Why would I want to go to pound force? Well, if I've got mass, I want power. That's force, that's energy per time. That's force distance per time. So I want to go from mass to force. And this is going to leave me with pound force, feet per second. That's force times distance per time. So if I've got force times distance on top per time, that I should be able to get that to power. If you go look up, you will probably find 1 horsepower for every 550 pound force feet per second, foot-pounds per second. So if you divide this by 32.2 and divide this by 550, you should get horsepower of about 0.21 horsepower. How do I know that? Well, experience. But again, it comes down to what units would you like? By the way, always box in or underline your answers for me if you would, please. Make them easy to find. What units would you, and it's not, I'm sorry, it's 03. I saw 0.203 horsepower. 3 significant figures would be plenty. And we're going to have to stop there. Pick up on the next video.